All right, today's lecture is on the Biot-Savart Law, which is basically which is where magnetic fields come from. It describes how a small piece of moving charge produces a magnetic field at a given point. All right, and we're not going to use the Biot-Savart Law that much by itself, but it's the basis. It's where what we're going to learn the magnetic field around a long wire comes from. It's where the magnetic. It's how we're going to figure out what the magnetic field inside a coil of wire is or a solenoid. It all comes from the Biot-Savart Law. It's the most general way to figure out what the magnetic field is from a moving charge. So just a real quick look at the objectives. Oops, here we go. This is number 4 in objective D. Students should understand the Biot-Savart Law so they can deduce the magnitude and direction of the contribution to the magnetic field made by a short, straight segment of current carrying wire. And then in a problem that we're going to do later on, we'll be able to derive and apply the expression for the magnitude of the field on the axis of a circular loop of current. All right. So mostly this first one, though, the magnitude and direction of the contribution to the magnetic field made by a short segment of current carrying wire. So let's see. We start by saying this is all found experimentally, right? We can find, physicists have done many experiments and found that whenever we have a moving charge, a magnetic field is produced. And the law that we're going to write down and come up with today basically is based on all of these experiments. So if we have a current carrying wire, right, and the wire can be in any shape. It's much easier when it's a straight wire or a symmetric shape like a coil, like a solenoid. But no matter the shape of the wire that's carrying your moving charges, each segment of it is gonna contribute to the magnetic field at any given point P, right? Really at every point, but we're gonna focus on one point. Right? We know that a magnetic field or an electric field or any field, right, has a value at every point in space, the magnitude and direction. So let's take a look at here's an arbitrary wire. We've got current flowing through here. Here's our point P, where we want to find what the value of the magnetic field is, the magnitude and direction. And what we're saying with this Biot-Savart law is that we're going to break this current carrying wire up into a large number of small pieces of approximately straight wire, right? Each small piece of approximately straight wire is going to contribute something to the magnetic field at this point. And what we would do once we figure out the magnetic field from one piece, right, we would figure out from each of the other pieces and add them up, right? And that's the integral. So let's try to define what our variables are so that we can write down this law. So here's my little piece of current carrying wire here, and it's pointing in this direction right now, right down along the wire, and I'm going to call that ds. Oops. So ds is a small segment of this wire, and it points along the direction of the current, so along the direction of the wire. Right, and its length is this infinitesimally small length of the segment. It points along the wire. Let's say. So let me draw that better. So that's an arrow. That's ds, right? Is our length along the wire. We need another vector, and this should look familiar from when we did electric field. The vector that points from our segment of wire to the point P we're going to call the vector r. And r hat is the direction. So we say r hat here is the unit vector. Make sure I want to use the same form that's on the equation sheet here. Oh, I see. Okay. Let me call this what I called ds before. I want to use the same term that's on the equation sheet. I'm going to change it to dl. So so a little length. Sorry, that's
Is r hat the direction or the magnitude?
r hat
Distance between them?
Yeah, r hat's the unit vector, so it's just the direction. It's unit vectors always have length of 1. So it's the unit vector that points from the segment to point P. So remember, unit vector has length 1. And we're going to have r, the magnitude, right? So this distance here is r without the vector hat. Is the distance from the segment to point P. Okay. So DL, I call it DS. It's called DS in the Survey and Jewett book. It's called DL on the AP test and in your equation sheet. But either way, that means a little length of whatever wire we're looking at, right? It's infinitesimally small, so small enough that even if it's a curved wire, it's approximately straight. All right. So any questions so far about these variables that we've defined? There's nothing here too new. We've done similar variables with other laws before. Okay, so here's the Biot-Savart law. Right. So the magnetic field at point B, or the piece of magnetic field at point P that comes from this piece of wire, right? Remember, if we want the magnetic field at point P, we're going to need to integrate over the entire wire. So that's why this is dB and not just B. So this is a small piece of B coming from this small piece of wire. I'm going to put the constant in afterwards, but it's going to be a constant times the current, right? The more current we have, it's proportional to the current. The more current we have, the bigger the magnetic field is going to be. Then we've got this DL cross R hat. So we're taking the cross product of this element here, DL, with this direction R hat, right? So if we can see from this, if the current is pointing towards point P so that it's in the same direction as R hat, that's how we know we get 0 cross product when the two vectors are parallel. And we're going to get the biggest value for the magnetic field when the current is flowing in a direction perpendicular to the direction towards point P. So we'll see when we see the magnetic field of a long current carrying wire, what effect that really has. And just like the electric field, it falls off as we get farther away from the element, and it falls off like R squared. If we get twice as far away, if point P is twice as far away from our current element, the magnetic field will be 4 times as weak. That's just like with the electric field, right? If you get twice as far away from a charge, the electric field there is 4 times weaker, right? It's an R squared, inverse squared law. The only other thing we need to put in here is is the constant mu naught over 4 pi. All right. And we learned the mu naught is kind of the magnetic equivalent of epsilon naught. All right, so mu naught is known as the vacuum permeability. right? Just like we have epsilon naught, which basically gives us the relative strength of the electric force, mu naught gives us the relative strength of the magnetic field. And the value of it, and this is on your equation sheet right here. Right here, right? Just like we have epsilon naught here, we have the mu naught here, right? And it's 4 pi times 10 to the minus 7 Tesla meters per ampere. So mu naught equals 4 pi times 10 to the minus 7 . Okay, and I'll say that mu naught is to magnetism what epsilon naught as epsilon naught is to electricity. Just a universal constant, right? And the kind of the cool thing we see when we get to electromagnetism is this, there's a combination of mu naught epsilon naught, and it's 1 over, what is it, 1 over the square root of mu naught times epsilon naught gives us the speed of light, and that's where the speed of light comes from. And at the very end of the course, we'll see that.
Good question, mister. But is that a pi besides the 4?
Yeah, 4 pi. Yep.
Gotcha. Sorry, I usually do the straight line. I was a little confused.
No, yeah, that's right. Sorry.
No, it's so fun.
All right. Okay. Our other questions so far. I think so. I just kind of and we're gonna stop almost here today. Now that we have the Biot-Savart Law written down, I do want to say about it is you can use this to find out from basically any current or sets of current. This will give you the magnetic field, right? The Biot-Savart Law is the most general way to calculate magnetic field. Right? What I mean is it works for every current. Current distribution, let's say. Right, no matter what currents you have, you can use this to figure out the magnetic field, but it's also the hardest way to do it. So we're going to try to find easier ways when we're looking at more symmetric things to get our magnetic field from. All right, so that's why I'm not going to focus too much on using the Biot-Savart Law and doing the integrals. When you get into doing this in college, you'll have plenty of time to do that.
So is that 10 to the minus 9 or minus 1?
Sorry, neither, minus 7.
Oh, I'm sorry. My eyes are all broken today. I'm sorry.
That's fine, no problem. Any other questions about Biot-Savart? So what we'll do going forward is we're going to use this in another couple of lectures to figure out the magnetic field that we get from a long straight current carrying wire and also from a coil of wire. Those are the kind of the important magnetic fields to know. And the way we get those is going to come from the Biot-Savart Law. And then we'll also see Ampere's law, which is kind of a shortcut, kind of like how Gauss's law is a shortcut for finding the electric field. Right, so this is basically, we have Coulomb's law for the electric field, right? And we know we can always use Coulomb's law in superposition, no matter what kind of charge distribution we have. But if it's complicated, then we get a real difficult integral or a real difficult, integral to do. And it's the same thing with here, right? If we have an unsymmetric set of moving charges, this integral can get really nasty and difficult to do. But you can use a computer and always do it numerically. But we're going to be looking at more simple situations, symmetrical situations, which makes this integral either very simple or that we don't have to do an integral at all. All right. Any last questions or comments on Biot-Savart law? Okay.